Okay, so question 3 shows you this section of polyacrylamide, and this time it is drawn as a skeletal formula, but you can see it still has this obvious chain of carbon, 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 so you recognise it straight away as an addition polymer. And so you do the same thing to identify the repeat unit. You can just draw a bracket round the 2 carbon repeat unit, rather wobbly bracket, but you get the idea that that same pair of 2 carbons with whatever's attached to it is repeated n times along the chain. So that's the repeat unit, and as soon as you've identified that, it's very easy, oops, unless you drop your pen, to draw the alkene, because you just follow the normal recipe and say, right, here's my alkene, and the things on the 4 corners, well, of course you can't see them, but they're hydrogen, hydrogen there, hydrogen, and then the amide group here. So you have H, 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 and then the primary amide at that position. So that's what acrylamide looks like. Acrylamide is not a proper systematic name, so we need to try and name that. So compounds which are primary amides like that just have names ending in amide. So for example, if we had that, that would be ethanamide, because you've got 2 carbons, one of which forms part of the amide group. So this one has got 3 carbons, so it's prop, and it's got an alkene group in it, so it's ene, and because if we're going to call it an amide, this is carbon 1, the alkene group starts at carbon 2, so it's prop 2 ene amide. And therefore the polymer, as always with addition polymers, you just put a bracket round that and stick poly in front of it, so it's poly prop 2 ene amide. Okay, so this is the cross-linked version of the polymer, and to pick this apart, the thing to do is, first of all, starting at this end, you can see that that looks like the normal repeat unit that you had in the previous simple polyacrylamide thing, as does that at this end of the other chain. So the interesting thing is now what comes next, which is again CH2 as you expect, but then instead of just the simple amide group, we get this rather complicated thing which links the next 2 together. So what we end up with is this cross-link like this, and then you get another normal polyacrylamide repeat unit like that. So this is the interesting bit which forms the cross-link, and the thing to do is to recognise that it's derived from an alkene group at the top and another alkene group at the bottom. So if we're going to draw out its structure, we just sort of say, right, we're going to have an alkene group at the top, and the usual thing, H, 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 and then we get this whole cross-link thing. So we have CO, NH, CH2, and then sort of mirroring that NH, CO, and then we're back to another alkene group, and so we can draw that in like that and stick the hydrogens on the end of it. And that's the compound that we need to make the cross-link, because it can continue the bottom chain by adding on here, and it can continue the top chain by adding on there using its 2 separate alkene groups, and of course it then, once that double bond opens up at each end, it can continue each of the chains as well. So that's what the cross-linking compound looks like. Now that's a hard question, don't worry too much if you didn't get that, but it's the sort of thing they could throw in just to really get you to think about things a little bit. Okay, so that's compound K. Okay, so moving on to question 4. This is the fragment that it asks you to interpret, and this time it's not an addition polymer, because you can see that as you go through the backbone it doesn't just have carbons, it's interrupted by oxygens. In other examples those could be NHs, and that's the hallmark of a condensation polymer. So this is a condensation polymer this time. And they really fall into 2 types. There are ones formed from a single monomer, which contains a carboxylic acid group and then either an alcohol or an amine group, and then you can just make lots of copies of that single polymer. But then there are ones, of which this is an example, where you have two different polymers, and the way you identify that it's one of those is that you see this pattern, that you get a pair of carbonyl groups with just carbons in between them, and then you get a pair of oxygens, or it could be NHs, again with just carbons in between them. Now, of course, in this case, because of the way it's been drawn, you can't immediately see the pair of oxygens, but you can see it if you just add on the next repeat unit, because obviously you can do that just by starting to draw this again. And so if you just add that on the end, you can see that as you extend the polymer again, you are going to get this section formed with a pair of oxygens. So when you get that pair framing some carbons and then that pair of carbonyls framing some carbons, that's how you tell that it's a condensation polymer formed from two different monomers. So what are the monomers? Well, they correspond to a dicarboxylic acid, so the pair of carbonyl groups will come from a dicarboxylic acid. So you just copy out that little section and you stick OH on the end at each end, and that gives you the dicarboxylic acid. And then again you copy out this section with the oxygens, and those oxygens come from OH groups, so from alcohol groups, and so those would be your two monomers in that case. You do the same thing if these were NHs to form a polyamide, and again you just add the extra H on the end to make primary amino groups. So why are they called condensation polymers? Well, because each time you add one of these monomers onto the growing chain, you have to eliminate a water molecule. It doesn't have to be water, it could be another small molecule like HCl, but condensation means each time a monomer is added to the chain, a small molecule is eliminated. So the balanced equation, we're going to need n of these, where n is a big number, so n of the dicarboxylic acids plus also n of those, so n of the diol, and then that's going to give you a really big repeat unit because it's got to cover all of that. So we can just, where the carboxylic acid group is, just convert that into the CO, because remember the OH has been lost, so we get this, and it includes this, so again the hydrogen's been lost there, so we just have O, CH2, 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 and then O, and then as always you put the linker bonds on the end, and that's repeated n times. But what you have to remember, and this is what people tend to forget because they sort of relax and congratulate themselves on having got the big repeat unit sorted out, but you've got to remember that it's condensation, so water has been produced as well, and there will be 2n waters produced, because there's one produced when the middle of the chain condensed together, so in other words when that ester group was formed, but then there's another one when this added on to the rest of the chain here, so 2n waters.